Hello everyone, welcome to Theory of Programming. In this video, I'm going to explain the most fundamental graph search algorithm, the breadth first search, or commonly known as BFS. Like there's an input and output to every algorithm, for breadth first search, our input is a graph G and a start vertex S. Our graph exploration begins from this input start vertex S. So the rough pseudocode of BFS looks like this. We will polish this pseudocode later, but this piece of pseudocode states how BFS explores a given graph. First step, we will add the start vertex to a queue. Second step, we will remove an element from the queue. Third step, we will add all its unvisited adjacent vertices to the queue. And then we repeat from step 2 until there are no vertices left in the queue. Now, it is totally okay if you don't understand it right now. So let's dry run this pseudocode with an example to understand it better. So this is our initial state before the graph exploration begins. We will mark vertex 1 as visited. I indicated this in my figure by coloring vertex 1 as green. Now we will add it to the queue. So the queue will currently hold one element, which is vertex 1. As the queue was not empty, we will enter the outer while loop. Now we will remove the topmost element from the queue, which would be vertex 1. So the variable current vertex will have the value of 1. Now we look at each adjacent vertex to vertex 1. Only vertex 2 is adjacent to vertex 1. So we will enter this for loop with the variable adjacent vertex having the value of 2. Now, as vertex 2 was not marked as visited, we will enter the if block. So we will add vertex 2 to the queue and mark vertex 2 as visited. I have indicated this by making vertex 2 green in color. Now we enter the second iteration of the outer while loop. Our queue had vertex 2, so this will be removed and the variable current vertex will now hold the value of 2. Now we look at each adjacent vertex to vertex 2. Since this is an undirected graph, vertex 1, 3, and 4 are adjacent to vertex 2. So let's iterate this for loop in that order. The first adjacent vertex is vertex 1. Vertex 1 is already marked as visited, so we don't do anything else now. The second adjacent vertex is vertex 3. Since vertex 3 was unvisited, we enter the if block. We will add it to the queue and mark it as visited. The third adjacent vertex is vertex 4. Since vertex 4 was also unvisited, we enter the if block again. We will add vertex 4 to the queue and mark it as visited. So currently our queue will have two elements, vertex 3 and vertex 4. Queue is the first in first out data structure. So pulling out the topmost element from the queue will give us vertex 3. So the variable current vertex will now hold the value of 3. Now we look at each adjacent vertex to vertex 3. Vertex 2 and vertex 4 are adjacent to vertex 3. Let's iterate this for loop in that order. The first adjacent vertex is vertex 2. Vertex 2 is already marked as visited, so we don't do anything else now. The second adjacent vertex is vertex 4. Vertex 4 is also marked as visited, so we don't do anything again. Since our queue had vertex 4 left, we enter our next while loop iteration. So removing the only element left in the queue, the variable current vertex will now hold the value of 4. Now we look at each adjacent vertex to vertex 4. Vertex 2 and vertex 3 are adjacent to vertex 4. Let's iterate this for loop in that order. The first adjacent vertex is vertex 2. Vertex 2 is already marked as visited, so we don't do anything else for now. The second adjacent vertex is vertex 3. Vertex 3 is also marked as visited, so we don't do anything again. Now our queue is empty, so we don't have another iteration, so we're done. This is how you explore the vertices of a graph in a breadth first search manner. If you notice, what we did was recursively explore all the neighbors of a given vertex until we ran out of new neighbors to visit. That was all fine, but we were just blindly visiting the vertices in the graph. So our previous pseudocode had input, we did some computation on it, but we didn't generate any valuable output. So we will polish our pseudocode now to store some information while we are exploring the graph. This information could be used to solve some popular graph problems. This is the complete pseudocode for breadth-first search. It is not very different from the one we just saw. The only difference is that we now have two input arrays, parent and level, and we will populate these two arrays as we keep exploring the graph. The parent array tells you via which vertex did you reach a given vertex through BFS. Let's say you reach vertex 2 for the first time via vertex 1, then parent of vertex 2 would be 1. The level array tells you how many edges away a given vertex is from the start vertex. So let's dry run this pseudocode with an example to understand it better. This is our initial state before the graph exploration begins. Again, let's say our start vertex is 1. Level and parent arrays both are as long as the number of vertices in the graph. So you'll have one entry in level and parent array for each vertex in the graph. We will initialize our level and parent arrays to -1. Now we will mark vertex 1 as visited. As usual, I indicated it in my figure by coloring vertex 1 as green. But we will need to know it programmatically as well. So for this we will use our level array. Any vertex whose level is -1, it will be considered as unvisited. And if it is not -1, then we will consider that vertex as visited. So initially we will set the level of vertex 1 to 0. Setting the level of vertex 1 to 0 makes sense because if you remember, I stated that level array will tell you how many edges away is a given vertex from the start vertex. So vertex 1 being the start vertex itself means it is 0 edges away from the start vertex. And as usual, we will add vertex 1 to the queue. Let's assume one indexed arrays for simplicity. So the first element of level and parent array belong to vertex 1 and so on. As the queue is not empty, we enter the outer while loop. Now we will remove the topmost element from the queue, which would be vertex 1. So the variable current vertex will have the value of 1. Now we look at each adjacent vertex to vertex 1. The only adjacent vertex to vertex 1 is vertex 2. Vertex 2 is unvisited since its level was -1. So we enter the if block and add vertex 2 to the queue. Now the level of vertex 2 would be whatever the level of vertex 1 is plus 1. So the level of vertex 2 becomes 1. And that makes sense since vertex 2 is one edge away from the start vertex, vertex 1. This is generalized by marking the level of an unvisited adjacent vertex as the level of current vertex plus 1. And as we reach vertex 2 from vertex 1, we will mark its parent as vertex 1. This is generalized by marking the parent of the unvisited adjacent vertex as the current vertex. Now we will enter the second iteration of the outer while loop. Our queue had vertex 2, so this will be removed and the variable current vertex will now hold the value of 2. Now we will look at each adjacent vertex to vertex 2. Since this is an undirected graph, vertex 1, 3 and 4 are adjacent to vertex 2. So let's iterate this for loop in that order. The first adjacent vertex is vertex 1. Vertex 1's level is 0, so we don't enter the if block. The second adjacent vertex is vertex 3. Vertex 3's level was -1, so we enter the if block. We will add vertex 3 to the queue and mark its level as 2, since the level of vertex 2 was 1. And since we reach vertex 3 via vertex 2, we will mark the parent of vertex 3 as 2. The third adjacent vertex is vertex 4. Vertex 4's level is also -1. So we enter the if block. We will add vertex 4 to the queue and mark its level also as 2. And similarly, since we reach vertex 4 via vertex 2, we will mark the parent of vertex 4 as 2. Now, pulling the topmost element from the queue will give us vertex 3. So the variable current vertex will now hold the value of 3. Now we look at each adjacent vertex to vertex 3. Vertex 2 and vertex 4 are adjacent to vertex 3. Let's iterate this for loop in that order. The first adjacent vertex is vertex 2. Vertex 2's level is 1, so we don't enter the if block. The second adjacent vertex is vertex 4. Vertex 4's level is 2, so we don't enter the if block again. Now, removing the last element left in the queue, the variable current vertex will now hold the value of 4. Now, we look at each adjacent vertex to vertex 4. Vertex 2 and vertex 3 are adjacent to vertex 4. Let's iterate this for loop in that order. The first adjacent vertex is vertex 2. Vertex 2's level is 1, so we don't enter the if block. The second adjacent vertex is vertex 3. Vertex 3's level is 2, so we don't enter the if block again. Now our queue is empty, so we're done. This is how we populate the level and parent array while exploring the graph by breadth first search. Using the level array, we can tell how many edges a given vertex is from the source. And due to the way in which BFS works, this number would be the shortest distance from the source to the given vertex. The parent array can be used to tell the shortest path from a given vertex to the source. We can construct this path by recursively looking at the parent of the given vertex till we reach the source. Example, take vertex 4. Parent of vertex 4 is 2, and parent of vertex 2 is 1, and parent of vertex 1 is minus 1. Now, only the source node will have its parent as minus 1. So this forms the path 1 to 2 to 4. Remember that these paths will be valid shortest paths only if the graph is unweighted. If your graph is weighted, you'd have to use algorithms like Dijkstra's algorithm or Floyd-Warshall algorithm. Now, as an exercise, try to compute the parent and level arrays for this graph, given that your start vertex is vertex 1. I'd recommend you to pause this video now and dry run the pseudocode we discussed just now for this graph. This is how your level and parent array should look like. If you've got it correct, then well done. If you've tried and got it wrong, it's okay. Try to see what went wrong so that you can do your future examples perfectly. Talking about the performance, the time complexity of breadth first search is order of v plus e. This is because the outer while loop runs once for each vertex, adding order of v time complexity, and the inner for loop runs once for each edge, adding order of e time complexity. The space complexity of BFS is order of v because we are using a queue where each vertex would get added once. Now, I want to talk about a slightly advanced topic. So this was our old unpolished pseudocode for BFS, which just demonstrated the way in which BFS explores the graph. If I restrict the discussion to just the way in which different graph search algorithms explore the graph, then as you know, BFS uses a queue to explore the graph. Now, keeping everything the same, if I just use a stack instead of a queue, then this becomes the depth first search algorithm. And if I use the priority queue instead of a regular queue, then this becomes a star search algorithm. Like I said, if I restrict the discussion to the way in which these algorithms explore the graph, then the only difference between these algorithms is the data structure they use. This is why I put you through the process of understanding the way in which BFS explores a graph first. Because if you truly understand the fundamentals of BFS graph search, you already know more than 80% of these algorithms. You add just a little code to these pseudocodes and they would become complete DFS and A-star search algorithms. So the next time you feel A-star search sounds so complicated, remember it is just BFS in disguise. As it is said, get your fundamentals right and everything will be a breeze. And BFS is the most fundamental graph search algorithm. So I hope my explanation so far made sense. Do comment if you have any doubts. So this is the code for breadth first search using a queue in C++. The codes are available on my GitHub. I will leave a link in the description below. So let's begin with the main method. I start off by scanning the number of vertices and the number of edges. I scan it to an adjacency list, which is a vector of list of integers. Then I scan the edges v1 to v2 and add it to the adjacency list, which will be an undirected graph. And then I go ahead and print my adjacency list to see if I got my input correctly. Then I created my parent and level arrays and initialized them. Here I am scanning a source vertex for my BFS method and calling the actual BFS method here. Then I am printing the output level and parent arrays here. Then I'm scanning a destination vertex so that I can print the path from the source to that destination vertex using the parent array. So now let us look at the BFS method. As expected, the inputs are the graph, the parent array, the level array, and the start vertex. I have created a list iterator which will allow me to travel this list of adjacent vertices. I set the level of start vertex to 0. I create my queue which is implemented as a list of integers, and then I add the start vertex to the queue, and this is my while loop, inside which I take a look at the front element and explore all the vertices adjacent to it. This if block is exactly as per the pseudocode. We populate the level and parent arrays and then add the unvisited adjacent vertex to the queue. And then I am popping my front element from the queue here, since the method front I used above doesn't actually remove the front element. Then coming to this method, print path from source to destination, it takes the parent array and a destination vertex as the input. As per my explanation in the video, all it does is recursively print the parent of the given vertex until we reach the start vertex. So as you know, the parent of the start vertex would be -1. So when we reach this condition, we deduce that we have reached the source vertex. If not, we just recursively look at the parent of the current vertex and print it. So let's run this code. As an input, I will give it the example graph I gave you as an exercise. The start vertex will be 1 and we will print the path to vertex 7. So as you can see, the level and parent array values will match those I have mentioned in the solution. And below, we have printed the path to the destination vertex 7, which is 1 to 2 to 3 to 7. Thanks for watching. If you found this video helpful, please hit the like button, and if you like the content on my channel, please hit the subscribe button and the little bell next to it so that you get notified whenever I post a new video.